So Coxeter groups, that's the topic of the course. And the idea of Coxeter groups is that Coxeter groups are a very, very nice family of groups. So you all took courses in group theory. You probably have favorite groups, least favorite groups, and I hope that by the end of the semester, Coxeter groups will be your favorite groups. That's my goal for the course. Coxeter groups are really very interesting. One very nice aspect of them is that really you can and you should think about them in terms of combinatorics, in terms of algebra, and in terms of geometry. And really, if you want to get a full understanding for them, you really have to think about them in the three ways. And you might see this as an opportunity if maybe you like algebra very much and feel a little bit shaky in geometry. Well, it's good because then you can take one aspect to really start understanding the other one. And so this is one thing that I want to emphasize is the whole time think about things algebraically, geometrically, combinatorially. And to give you an idea of how that goes, what I want to do for the first class is talk about a group that you already know and show you how we can think about this group in these three ways: combinatorially, algebraically, and geometrically. So that's the first thing we'll do. We're going to talk about three ways of thinking about the symmetric group S3. I think this will give you a good idea of what Coxeter groups are more or less about. Okay. So there's a way in which you have all thought about the symmetric group, and you might not know that this is a combinatorial way of thinking about the symmetric group, but that's what I want to show to you now. So we think of the symmetric group as basically ways of shuffling elements of a set around. Right? So the elements of the symmetric group are the permutations of the set of numbers from 1 to 3. Throughout the whole course, I will call this the number in brackets, in square brackets. That will mean the numbers from 1 to n. And, well, this is small enough that we can make a list of them. 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. But to give you a group, I cannot just give you a set. I have to tell you a way in which you operate the elements of the group operation. So the operation of S3 is what we call composition of permutations. Okay? And so let's do that in an example. Maybe you haven't done this in a while, so I want to do it quickly. I want to do it slowly, sorry. And this is one of these things that is kind of like a you want to see me do this as a movie, so please look up, stop writing, and let's remember how you operate elements in S3. What you do is you say, okay, with the first number here, what I'm going to do is see what the first number is here, 1, and then look for that position in here, 2. Okay? So to figure out what this first number is, you go here to the first position, and you find that it's a 1, and that means that you go to the first position, and write down a 2. Okay? Then to get the second one, you go to the second position, which is a 3. And then this means that you should go to the third position here, and put a 1 here. Okay? And then for the third position, You go to the third position of the second permutation, 2, and that means that you should put a 3 here. Okay. Is that clear what I did? Any questions about it? I always have to remind myself every time I do this, so don't feel bad if you don't remember and missed it. Feel free to ask me. So that's how you operate permutations, and it's a fact of permutations that when you do this, what you end up with is a permutation again. Okay. So these are the elements of the permutation group, and this is the operation. John.
I'm sorry. Can I ask you not to use that red marker?
Sure. Yeah. So let's use. Okay. So 1, 3, 2. Let me use a bold 1, 3, 2 then, because I really want to distinguish between these. Okay, so this is supposed to be bold. I want to show you another way of thinking about this that is very useful. Do you have a question, Jack? Or? No. Okay. So one way of thinking about permutations that is very nice is through wiring diagrams. Okay. So for example, let's write this bold permutation as a wiring diagram. 1, 3, 2. Okay. So in a wiring diagram, what you're going to do is put 1, 2, and 3 on top, 1, 2, and 3 in the bottom, and then you're going to just take wires that tell you to go from here to here. Okay. So actually, if you don't mind, I'm going to a better example is the other permutation. You'll see why in a second. So let's do 2, 3, 1. So the wiring diagrams takes the first position to 2 because there's a 2 here, the second position to 3, the third position to 1. And that's the wiring diagram of my permutation. Okay. And so what's the use of thinking about it in this way? Well, the thing is that now we can think about the operation in a different way. Okay. So let's operate using wiring diagrams. So let's say that I want to now operate 2, 3, 1 and 1, 3, 2. Okay. Well, one way of doing it is the following. Let's take the diagram of 2, 3, 1 and of 1, 3, 2. Let me put the one of 1, 3, 2 on top. Okay, so 1, 3, 2 goes from 1 to 1, from 2 to 3, and from 3 to 2. Okay. And let's take the wiring diagram of 2, 3, 1. So this goes from 1 to 2, from 2 to 3, from 3 to 1. Okay. And if I want to operate these two permutations, then all I have to do is stack these guys on top of each other. So let me do that. Here's the top diagram. Here's the bottom diagram. Okay? And then you just regard this as a wiring diagram that says, what does it say? It says, go from 1 to 2, from 2 to 1, and from 3 to 3. Yeah? So I get 1 to 2, 2 to 1, 1 to 3. And so I get the same result as before. Now you should think about why this works, and you can imagine that it's not very hard because we haven't really done very much. So what I want you to think about is why what I'm describing here is exactly the same thing as what I did here. It's just kind of a cute way of doing it, but it's a useful way, as we will see. We will see why these wiring diagrams are useful. Okay? But this allows us to do this operation in this group in a very combinatorial way by just taking these pictures and stacking them on top of each other. Okay? And this is why I want to say that this way of thinking about the symmetric group is very combinatorial. Okay? Maybe just very quickly, another way in which you might have seen the symmetric group described is that you have a stack of cards. And then elements of the symmetric group are just rearrangements of the stack of cards. Yeah? So here you have the cards in the order 1, 2, 3. And then the wiring tells you, now put the first card in the second position, the second card in the third position, and the third card in the first position. And so you can think of elements of the permutation group as shufflings of the cards. And the operation just means shuffle according to the first permutation and then shuffle according to the second permutation. Okay? So that's combinatorics. Any questions about this point of view? All good? Okay, so you might have thought that because you've seen the symmetric group in an algebra course that was algebra. But let me show you a more algebraic point of view on how to think about this group. What I want to do is that I want to define my symmetric group now in terms of generators and relations. And we'll see what that means. But what I want to say is that the symmetric group has S3 has two generators, which I'm going to call A and B. And relations. Okay? The relations are going to be the following. What I mean by this is that your generators are A and B, and you should think that the elements of the group are obtained by multiplying these guys in some order. Whenever I say multiply in this course, I'm going to mean operate, of course. So, for example, an element of the group might be A, B, B, A, B, A. Okay? But I'm going to give you some relations. So, one relation is that A squared is the identity. Another relation is that B squared is the identity. And the last relation is that ABA equals BAB. Okay. So these are the three relations that I'm going to introduce between A and B. Okay? And given this, I'm going to define a group in the following way. I'm going to say now, the elements of the group are going to be what I described to you, words in the alphabet AB. But this is not exactly right, because if you think about it, I mean, this is right. These are the elements, but they're repeated. Because, for example, the word AA is the same as the empty word. Or the word BB is the same as the empty word. Or the word ABA is the same as the word BAB. So I want to say that the elements are the words, but they're modulo the relations. Okay? What I mean by that is just what I'm telling you. You should consider the word ABAB as the same as the word BABB. And now what's the operation? If I give you one word and another word, then the way you operate them is you just glue them together. Sometimes you'll see this called concatenation, but don't be scared of that big word. It just means glue them together. Okay? So that's my group. The elements are words. Operation is gluing. But now you might be a little bit surprised or confused or something, because if you think about it, I'm giving you a list of elements, and this list is infinite, right? Because you can make infinitely many words in A's and B's. And so the way that I'm describing this, you might think that this group is infinite, yeah? But somehow I'm saying that it's S3. And so let's investigate this. Let's understand why this group that would seem infinite from this description, actually it's not only finite, it's very small. It only has 6 elements. So let's understand why that is. Well, the thing is, let's see what happens when I take some big word like, I don't know. I'm gonna go down the room and everybody's gonna tell me a letter. So B, Eric, A. Actually, let's stop here just so it fits on the board. Okay. So that's a word. That's an element of the group. But now, if you think about this, well, actually, let's do it a little bit more complicated. Let me do this. Okay. So this is an element of the group. But the thing is, you can this element has many names, because whenever I apply a relation like this, I get a different name. And we can see that, for example, here I have a b squared. B squared is the identity, so I can just forget about this. I'm multiplying by the identity. That doesn't do anything. A squared is the identity. Here, you can either take this a squared or this a squared. It doesn't matter. That's the identity. And so what I'm left with is a, b, a, b, a, b, b. But then you see, actually, I can keep simplifying, right?
You only have one B at the end.
Did I? Let's say I had another one. Well, no. Okay. I only had one B. So this is what I get. So what should I do now? Well, I can simplify this a little bit further, because if I switch ABA to BAB, yeah, I take this ABA, and that is the same thing as BAB. And why is that a good idea? Because that means I can reduce it further. So BB goes away, and I get BAAB. Now AA goes away, and I get BB. And now BB goes away, and I get the identity. Okay.
So order doesn't matter here. How we do it, though?
There's a lot of implicit questions. Does it matter that I first canceled here and then here, or here and then here? We'll prove that it doesn't matter. But that's a very good question, and I haven't proved it to you yet. Okay. We'll see why. But if you believe me that order doesn't matter, then what I just proved to you is that this element that we thought was very big actually is the identity. And this explains to you why this group maybe is not so big at all. Yeah? And actually, let's see if I have time. Let's actually prove that this only has 6 elements. So I'll let you think about that a little bit while I erase this board. Why is it that this group only has 6 elements? Maybe I'll ask you first, why does it have only finitely many elements? Any ideas?
So if you have a bunch of A's next to each other, you're going to get some reduction. And if you don't, then you have an A, B, A somewhere. You can flip it, and you'll be able to reduce.
So maybe that's the first thing I can do is, no matter what word I'm given, I can always take the repetitions away. Right? So if I take a big word.
Sorry, our words are assumed to be finite words, right?
Yeah, that's a good point, actually. That's a very good point. I should have said here that the words are of finite length. Okay? There's infinitely many of them because the length could be as big as you want, but each one of them has a finite length. So, given a word W in this group, the first thing I can do is take away every repetition that I see. Repetitions AA and BV. And if you think about that, when I do this, what I'm going to be left with is always a word that looks like this: AB, 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 or BA, BA, BA. But so I'm left with something like A, B, A, B, etc., or B, A, B, A, etc. But there's still infinitely many of these. So how do I know that that there's finitely many? So this is when Aaron is telling me, well, what you can do now is, if you have 3 guys like this, you can switch them. So if you have ABA, you can make that into a BAB, and now cancel the B and the B and get something shorter. So that's the second thing I can do, is if I have more than 4 letters, so if I have something like AB, AB, etc., then what I can do is take this ABA and make it into a BAB, etc., and now reduce the 2 B's. Okay. And if this has more than 4 letters, then I repeat that, and I keep doing this. So what we're showing here is that you never need 4 or more letters. Every word here can be expressed using at most 3 letters. And that means that the possible words are the empty word, which is the identity element, the word A, the word B, the word AB, the word BA, the word ABA, and the word BAB, which is ABA. I'm sorry? So let's call them the possible irreducible words. Okay. The words that you cannot make any shorter. There's 6 of them. Okay. How do I know that this is the symmetric group then? How many groups of order 6 are there? You guys remember? I know some of you took my class last semester, but I won't point to you. Anyway, I mean, this is, you might or might not remember. So there's 2 groups of order 6. One is the symmetric group. One is the cyclic group. And there's a very easy way to tell them apart, which is that the cyclic group is abelian, everything commutes, and the symmetric group is not abelian. Okay? And here, this is not abelian because AB and BA are different elements in the group. Okay? So 6 elements, not abelian. That means that this must be the symmetric group S3. Okay? Now, I don't know if you find this proof satisfactory. I find it a little unsatisfactory because we haven't really understood why this is S3. We have this indirect proof that shows, okay, well, it has 6 elements, it's not abelian, so it must be S3. But it would be better to understand why I really can understand that these are permutations. Okay? And the way to understand it is the following. The thing is that you can think of A as this element of the symmetric group. Okay? So this is the wiring diagram that switches 1 and 2. And I can think of B as the wiring diagram that keeps 1 alone and switches 2 and 3. So these two guys are certainly elements of the symmetric group. And now let me show to you that they satisfy the relations that that they're supposed to satisfy. Well, this is kind of fun. We can just do it. So what's A squared? We stack the picture for A with the picture for A. And so we see that goes from 1 to 1, from 2 to 2, from 3 to 3, the identity. Okay. B squared, you stack the picture for B with the picture for B. 1 to 1, 2 to 2, 3 to 3, the identity. Okay. What about A, B, A? Well, what we have to do is stack the picture for A, the picture for B, the picture for A. Okay. And this is the permutation 3, 2, 1. Okay. And actually, I'll leave it as an exercise for you so that you practice with this stuff to check that if you do BAB, you get the same thing. So exercise, do this for BAB, and you'll see that the wiring diagram looks different, but it matches the top and the bottom in the same way. So that's the same permutation. Okay. So this actually explains to you why these two guys are the same group. And still, I mean, there are some things that I haven't proved entirely to you, but what I want to do today is just give you an idea of why these things are the same. Okay. We'll give rigorous proofs next time. Any questions about this? Actually, I have a question for you guys. Why is it that every permutation can be expressed as A's and B's? Okay. If I tell you A is what I said it is, B is what I said it is, then why is it that every permutation can be obtained by just doing A's and B's? So think about that. That'll be the first question on the forum of the course. But really do think about it. Okay. So maybe I'll even, let me just put a little box here, and it's a question to think about. Why can every element of S3 be written as a word in A's and B's?
In general, in SN, you need n-1 letters in your alphabet.
And we'll make that the next question in the forum. What about SN? Can we generalize this to SN? It's a very important question, as we will see. So finally, let's talk about geometry. So what's a geometric way of thinking about the symmetric group S3? Well, this, I hope I'm able to draw this. So the challenge is to draw a 60-degree angle. Maybe that's about 60, I don't know. I learned this from my little nephew, actually. So I was playing with my little nephew, and he loves mirrors. And he really likes standing in between two mirrors. So you should think that this is a mirror, this is another mirror. And then he was really playing with the mirrors and seeing what happened when he played with the mirrors. And he found that as he moved the mirror, there were more or fewer copies of him that he could see. And his uncle's thinking about math while he's doing this. I don't know if that's fair, but I mean, he likes 60 degrees. Or maybe I like 60 degrees. For the following reason. Where's my... Here. So here he is, looking towards the mirror. So you should imagine that's him. I can't really draw. And he found that, or I found that, when the angle was 60 degrees, then he could see exactly six little babies. Okay. So why is that? Let's understand why that is. Well, where's one copy of himself? Well, if he looks here, then he can see that there's another little baby right here, looking at him in the eye. Right? But if he looks at this mirror, then this is where it gets tricky to draw. But there's another baby right here. That, we'll see, he's looking away from his image, so his image is looking away from him too.
So those two are perpendicular to that line.
Right, and this is perpendicular to this line, and this is perpendicular to this line. But there's other ones, because, for example, there's an image. Where's the other one? So, for example, he can see, if he looks over here, he can see his reflection on this mirror of this guy. You should really stare at this picture for a while until you understand it. What ends up happening is that you get something like this. And the 6, his name is Miles. So the 6 miles that he sees are like this. There's another one here. There's another one here. And another one here. Okay.
I can only understand the first two. How do you get those other three?
You know, I can kind of point here, but that might be more confusing. But just imagine if you look from here to here, if you look in this direction, follow the mirrors around. If you look from here to here, you run into this mirror, which sends you in this direction, and then you think you see this guy, and really you're seeing this guy. So it's like a triple reflection of, it goes from here. Actually, we'll see. I'll show you how.
So when they hit a mirror, they go off angle of reflection equals incidence reflection.
Exactly. Well, what does this have to do with a symmetric group? It has to do a lot, as I will show you, because if we call this mirror A and this mirror B, and we call the real Miles the identity, okay, then reflecting across A, we get a Miles that's called A. Reflecting across B, we get one called B. What about this one? What should I call, what should I call this Miles? I can't think of him as reflecting across here because I don't have a name for this guy. Instead, let's think that this is the reflection of A across B. Okay, so I'm going to call it B A, meaning you first reflect on A, then you reflect on B. If we do it the other way, if you first reflect on B and then reflect on A, you get this Miles. Okay. Now, if I reflect this guy across the mirror B, I get BAB. But I can also think of this Miles as the reflection across this mirror, which means taking this guy and reflecting across A. So that's also ABA. And then you see it. What does A squared mean? I mean, the way this works now, you can really think of these as a room with 6 rooms with mirrors. Okay? And let's just call reflection across these mirrors A, reflections across these mirrors B. Okay? So A squared means reflect and reflect back. You didn't do anything. B squared means reflect and reflect back. You didn't do anything. And then to understand that other relation, ABA equals BAB, well, you go ABA equals BAB. And you find that you get exactly the same reflection. Okay? So what that means is that I have now two geometric operations, the operation of reflection across this line and the operation of reflection across this line. And these geometric operations are actually a geometric realization of this group. So I can really think of A as reflection across this guy A. B. I actually want to, well, no, B as reflection across B. And this gives us a geometric realization of the symmetric group. S3. Okay. Where A squared equals the identity, B squared equals the identity, and ABA equals BAB. In this context, they're really geometric facts about the way that reflections behave. Here they reflect geometric facts. Okay. Any questions about this? I really, really encourage you to think about this more carefully. And I mean, I've drawn this picture several times, and now I feel like I can see it. But really, the only way to really get it is to just draw it and stare it and label it, and then erase it and draw it again until you really see it.
Like in that diagram, Federico, could you draw lines that would take us from E to AB? Could you draw lines that we could get from
From E to AB?
Yeah.
You could draw a line. I mean, what this line really is supposed to, you should interpret it in this way, that if Miles looks in this direction, then you see what he's going to find is that then he's going to go off towards this reflection of himself, but then really he's going to hit this mirror and see this reflection of himself, which is really him. No, sorry. See, that's why I tell you the only way is to draw yourself. You look towards here, but then really what he's going to see is the reflection over here, which is really this reflection. So what he's seeing is the reflection of here to himself. Okay? And you should do this for all of these images. Okay. So this is just a little preview of the course of how you think about Coxeter groups, and really the symmetric group I think is a very nice example that motivates a lot of the theory. But the general nice thing about Coxeter groups is that you can really think about them in all of these ways, and that gives you a lot of tools to work. Okay. So let's stop there. See you guys next time.